Okay, so I think it's worth saying something about how this Yoneda correspondence um, matches up with another way of looking at these functors into set, which is in terms of a left action. So we can think of a functor G from C to set as a load of kind of elements of this thing corresponding to G that have different sort of internal types, like this one here has an internal type of capital E because it's an element of G of capital E. And then when the internal type of one of these elements, like this little e here, matches up with the domain of an arrow S of C, then we have a left action that we can perform. So a left action alpha is going to send S, comma E to alpha of S, comma E, which is just G of S of E, okay, which is going to be a member of G of V. So this is sort of similar. So this idea of sending E to alpha of S, comma E is sort of similar. I mean, under the Yoneda correspondence, it's like sending epsilon to epsilon after H of S. And this is where we see one of the kind of benefits of the pre-sheaf idea, which is sort of applying this switch of the directions of the arrows in C, because in this context we haven't done such a switch, and there is a bit of disparity here because we're sort of doing a left action, but that's corresponding to composing with a kind of S at like arrow on the right. But you know, I think this is a small price to pay for actually for having beginners actually able to understand it. Whereas like pre-sheaves are pretty hard to get into because they start with this weird flip thing. Anyway, so we have this alpha. We can define it really as something that has to work on stuff corresponding to the domains of these arrows, and it has to be such that alpha of ID, comma E is E. So doing the left action using an identity returns the same thing. And also alpha of F after G, comma X is alpha of F, comma alpha of G, comma X, okay? And you can see that these just correspond to laws of like how functors work, basically. It's just an encoding of that. There's also something to say about natural transformations. Since we can basically define the functor category as like these collections of elements which are organized into according to different internal types, and then we have these kind of left actions that we can perform upon them. I mean, the reason it's left, by the way, we can think of it as matching up with the way we write this, but the real thing is that the composition sort of stacks up on the left as well, as you can see here. So maybe the normal way to write this, rather than, for example, writing alpha of G, comma X, people would probably normally write people would normally write G dot X. And so we've got that F dot G dot X is equal to F after G dot X, and that's an expression of this stuff. But I prefer to actually put the alpha in, keep it explicit. Now, Yeah, the other thing is about natural transformations. So consider a natural transformation beta from G to G dash. Now, this ought to be such that if we have an arrow S from E to V, and an element little e of G of E, we have this kind of commuting square because it's a natural transformation. And so if we follow this round, both sides of the square, up here we'd get beta E of E, and so on. And we get this equation here that going around the bottom left, beta V of alpha of S comma E, and going around the top right is equal to alpha of S comma beta E of E. And we can kind of, if we're thinking of these, well, I mean, Reyes would use a contravariant notation, but he also refers to these things as C-sets. Okay, but anyway, if we're thinking in these kind of terms, we may cross out these subscripts of our natural transformation. We can sort of think of that as a convention, but notice how similar this then looks to the expression in terms of the Yoneda lemma for how we'd talk about the same thing once we'd converted everything to natural transformations. And notice that this rule really just looks like associativity of composition of the natural transformations that represent the actions and C set elements and so on. So yeah. And then there's the question of how we actually use the Yoneda lemma. And we use it in loads of places. So since we're mostly interested in making this connection with the Mitchell-Benebaugh language, we can say, well, okay, it's true that these kind of functor categories that we're making, categories of functors into sets, they are toposes, so they do have sub-object classifiers. So to denote the sub-object classifier as omega, we're going to really show how to construct it. So an element little e of internal type capital E of the sub-object classifier omega corresponds to, under this Yoneda correspondence, it corresponds to a natural transformation epsilon from hom e comma blank to omega. And that's going to correspond then to a subobject A of hom e comma blank. So we find that the elements of internal type E in the subobject classifier just correspond to subobjects of hom e comma blank, which is pretty interesting. And then the other thing is how we do this sort of S action upon those things. What do we get? And so, like, take this element E, do G of S on it, so we're doing kind of S action on it. We've seen already that this corresponds to epsilon after H of S. This is under the Yoneda correspondence, but this is going to be an arrow into the subobject classifier omega, and therefore it's going to correspond to a subobject, which we call epsilon after HS star, and that's actually just going to be, as we see from this diagram, it's going to be the pullback of this A here, which is epsilon star. It's going to be the pullback of that along h of s. And that's going to be this b here, which is the thing that, okay, Sal, which is the thing that corresponds to doing the S action So, I mean, basically, if we're thinking of the elements of our subobject classifier as corresponding to these subobjects of hom e comma blank, then doing the S action on them corresponds to pulling back such a subobject along h s to the minus 1, along h to the power of s, okay? So h to the power of s to the minus 1 of a is the thing that corresponds to doing the S action on this A thing, which is like the thing that corresponds to this type E element of omega to the power of E. So we can look at examples and see how this gives us this precomposition way of thinking about doing updates in the category of dynamical systems.